Title: Low-Latency Privacy-Preserving Deep Learning Design via Secure MPC. Abstract: This paper proposes a low-latency secret-sharing-based MPC design that reduces unnecessary communication rounds during the execution of MPC protocols. It also presents a method for improving the computation of commonly used nonlinear functions in deep learning by integrating multivariate multiplication and coalescing different packets into one to maximize network utilization. The experimental results indicate that this method is effective in a variety of settings, with a speedup in communication latency of 10^20%. Keywords: multi-party computation, deep learning, privacy preserving. Introduction. Secure multi-party computation, MPC, enables parties to compute securely over their private data without revealing the data to each other. MPC offers privacy-preserving property, which makes it suitable for most privacy-sensitive domains, such as medical research and finance. The prospects of secure MPC demonstrate its application to secure machine learning and deep learning. However, most MPC-based deep learning frameworks suffer from limitations caused by network communication due to the nature of exchanging intermediate information during MPC execution and excessive computation introduced by complex MPC protocols. Methodology. The proposed method aims to reduce the communication latency of the MPC protocol through optimized multivariate multiplication. It utilizes secret sharing-based techniques to avoid extensive computational overheads. The approach is based on linear computations, such as addition and multiplication, which are inherent in modern deep learning techniques that rely on linear algebra. Contributions. 1. A low-latency secret sharing-based method for computing multivariate multiplications and univariate polynomials using network communication that is efficient and reduces unnecessary communication rounds on the fly. 2. A method for improving the computation of nonlinear functions by integrating the proposed multivariate multiplication and coalescing different packets into one to maximize network utilization. Experiments. The effectiveness of the proposed method was evaluated in a variety of settings. The results indicate a speedup in communication latency of 10^20%. In conclusion, this paper presents a novel approach to enhance the practicality of MPC-based deep learning frameworks by reducing communication latency and improving computation efficiency. This could potentially make MPC more feasible for real-world applications in privacy-sensitive domains. The authors propose a secure multi-party computation, MPC, scheme based on arithmetic secret sharing, which facilitates efficient communication among parties involved in the computation. This setup focuses on arithmetic operations, representing inputs and intermediate results as linear secret shares between n parties. They adopt a simple arithmetic secret sharing scheme based on n0 Shamir secret sharing, where a scalar value x is shared across n parties, and the ground truth value x can be reconstructed from the sum of the shares of each party. The authors explain how to represent floating point numbers using fixed point encoding, where each x is the result of multiplying a floating point number x_f by a scaling factor b and rounding to the nearest integer. To decode a ground truth floating point value x_f from x, the authors compute x_f approximately equals x, b. The authors then discuss how to implement secure MPC using arithmetic secret shares, which are homomorphic and can be used to implement linear computations. They describe how to perform addition and multiplication operations on secret shared values, including the use of beaver triples for secure multiplication. The authors also explain how to implement linear functions, such as elementwise product and convolution, by combining additions and multiplications. For nonlinear functions, the authors note that most works use approximation methods, such as Taylor expansion, Newton-Raphson, and Householder methods, to simulate the outcome of nonlinear functions using only linear operations. Finally, the authors provide notations used throughout the work, including the notation x for secret sharing of x and reveal x for revealing the ground truth value x to every party involved in the computation. The authors of this research paper delve into the realm of communication-efficient multi-party computation, MPC, and its application in modern deep learning frameworks. They aim to develop an MPC system that can efficiently compute beyond finite range, a feat not achieved by previous research focusing on polynomial calculations. Recent deep learning frameworks that preserve privacy, such as Secure-In, ABY3, Crypt10, and the MPC Transformer Inference Framework, are cited as precedents. The authors then detailed their methodology, particularly multivariate multiplication, which leverages arithmetic tuples computation. They extend Beaver triples to general Neri Beaver triples, reducing the number of communication rounds required for multivariate multiplication. This is achieved through pre-computing and pre-sharing auxiliary shared values to blind the inputs. The authors define sets of shared degree cross terms and the difference between the inputs and masks, leading to equations 1 and 2. Equation 1 represents multivariate multiplication as a product of terms, while equation 2 adapts this concept within a secret sharing scheme. This approach enables parallel communication and computation in a single round, significantly reducing communication latency and improving MPC efficiency for deep learning frameworks. The authors build upon previous work, including Knott et al.'s Crypt10 framework, to provide a low-latency linear MPC implementation. This novel approach has the potential to revolutionize the field of MPC in deep learning, ensuring privacy-preserving computations with enhanced efficiency. The authors introduce the multivariate Beaver multiplication protocol, detailed in Algorithm 2, which facilitates the multiplication of secret shared inputs with constant complexity. This protocol involves computing masked values, revealing them through one-round communication, and then computing the final result using pre-shared auxiliary sets. This approach reduces the total rounds of communication from n1 to a constant 1, albeit at the cost of increasing the overall size of communication data from linear to exponential. The authors also discuss the use of univariate polynomials, which enable efficient evaluation and manipulation of polynomial expressions. They propose computing all required secret shared inputs in parallel using multivariate multiplications and then multiplying them with corresponding plaintext coefficients. However, this approach has the disadvantage of exponentially increasing the size of transmitted data. An implementation of univariate polynomials is provided in Algorithm 3, which involves constructing base terms, iteratively exponentiating, and using vectorized Beaver multiplication. This approach allows for computing the polynomial expression efficiently. Finally, the authors discuss the optimization of nonlinear functions, such as exponentiation and logarithm, by leveraging the property of parallelization of the proposed multivariate multiplication. For exponentiation, they resort to the naive iterative approximation, which utilizes multivariate multiplication effectively. For logarithm calculation, they rely on higher-order iterative methods for better accuracy. The authors implement basic math operations within a secret sharing computation framework, including logarithm, reciprocal, and trigonometry functions. The logarithm function is computed using householder methods, which involves orthogonal transformations to tridiagonalize a matrix, enabling efficient calculation of logarithmic values. Meanwhile, the reciprocal function leverages the Newton-Raphson method, an iterative approach that converges to the reciprocal value through successive approximations. Trigonometric functions are treated as special cases of exponentiation with a specific value of d, allowing for efficient computation of trigonometric values. Notably, the authors introduce communication coalescing, a technique that reduces the total number of communication rounds among parties by combining independent communications into a single round. This approach optimizes network bandwidth utilization and enhances the efficiency of the computation protocol. A security analysis of the proposed method is also provided, demonstrating that multivariate multiplication is secure under semi-honest conditions. Specifically, the technique maintains the indistinguishability between random distributions and view distributions for each party, ensuring that no party can infer additional information beyond their designated shares. This robust security guarantee enables the proposed method to facilitate secure and efficient secret sharing computations. Lin et al. Have developed a novel approach to enhance the efficiency of multi-party computation, MPC, in deep learning models. By optimizing data transmission and computation time costs, they aim to improve MPC performance by reducing communication costs between parties involved in the computation. using the CRIP-10 framework as their basic MPC deep learning framework, which provides naive implementations of secret sharing-based computations. The authors conducted experiments with various deep learning models, including linear SVC, Lenant, ResNet-18, and transformer encoder, on different datasets such as MNIST, CIFAR10, ImageNet, and Sentiment 140. To evaluate the effectiveness of their proposed method, the authors adopted several metrics: computational time cost, TCOMP, communication time cost, TCOM, size of transmission data, and classification accuracy. They simulated different network environments with varying latencies: low, 0.1 milliseconds, medium, 5 milliseconds, and high, 40 milliseconds, and a bandwidth of 1 gigabit per second. The results showed that the computation cost of each model was negligible compared to the communication cost in medium and high latency network settings. The authors' proposed method reduced the communication cost in every network setting compared to the naive implementation of MPC, achieving an improvement of 1020%. This indicates significant enhancement in performance, particularly in high latency environments for practical purposes. The authors observed that their proposed method behaved differently with neural models of different architectures. For instance, the attention mechanism in the transformer model was constrained by its communication bottleneck in the softmax operation, while the CNN model in ResNet-18 was less affected. Overall, the paper presents a novel approach to optimizing the efficiency of MPC in deep learning models, focusing on reducing communication costs and improving performance in various network environments. The authors present a comparative analysis of classification accuracy using different methods, as shown in Table 2. The results demonstrate that the proposed method achieves comparable accuracy to the original and naive implementations across various datasets and models, including MNIST, CIFAR10, ImageNet, and Sentiment 140. Figure 1 illustrates the communication percentage of different models, highlighting the significance of convolutional operations, attention blocks, and nonlinear functions in the proposed method. Attention-based models exhibit a substantial improvement in latency, with a 25% reduction, whereas traditional machine learning and CNN-based models show limited improvement of 815%. The evaluation section examines the side effects and factors associated with the basic settings, including the downstream task's accuracy, the number of parties involved, and the trade-off between network latency and bandwidth. Figure 2 compares the drop in accuracy between the proposed method, the original baseline, and the naive implementation. The results indicate that both MPC-based implementations obtain lower accuracy in complex scenarios, with the proposed method performing slightly worse than the naive implementation. This is attributed to the multivariate multiplication introducing additional precision requirements, which reduce accuracy. The authors also investigate the impact of the number of parties involved on the throughput and latency of MPC-based methods. Figure 2a shows that the communication data size increases linearly with the number of parties, while Figure 2b illustrates the tendency for latency to worsen with an increasing number of parties. Furthermore, Figure 3 demonstrates how network bandwidth affects communication costs, highlighting the importance of bandwidth as a factor in multi-node MPC settings, especially as the number of nodes grows. The proposed secret sharing-based MPC method enhances linear computation in deep learning by introducing multivariate multiplication and communication coalescing mechanisms. These innovations reduce unnecessary communication rounds, resulting in a latency improvement of 1020% compared to naive MPC implementations. The method's validity and efficiency are demonstrated through experiments, showcasing comparable throughput and downstream task performance. This work aims to inspire future improvements in privacy-preserving deep learning techniques and practical MPC applications. Secure multi-party computation has become a crucial aspect of modern applications, enabling distributed machine learning while maintaining privacy and security. Recent advancements in cryptographic techniques have paved the way for efficient and private neural network training protocols. Secret sharing, circuit randomization, and homomorphic encryption are essential cryptographic tools for achieving privacy and security in distributed machine learning settings. The Falcon protocol, arithmetic tuples for MPC, and randomizing polynomials are fundamental cryptographic protocols that form the foundation of secure neural network training. Circuit randomization plays a key role in enhancing the efficiency and security of MPC protocols. Mixed protocols, such as ABI-3, combine different cryptographic techniques to achieve optimal performance and security. Advancements in deep learning, including residual learning, attention mechanisms, and normalization techniques, have significantly improved the accuracy and efficiency of neural networks, making them more suitable for real-world applications. Benchmark datasets, such as ImageNet and Twitter sentiment, are essential for evaluating the performance of neural networks. Fully homomorphic encryption has the potential to enhance the privacy and security of MPC protocols further. However, challenges and future directions remain, emphasizing the need for further research in developing more efficient and secure cryptographic protocols that can support large-scale machine learning applications.